Is it good? All right, cool. What's up, guys? So anyway, my talk is Fuzzing with AFL, American Fuzzy Lop, for those of you not familiar. It is a really fun tool. It's really polished, which is very unlike hacker tools in my experience. You use it and it just works. So, the obligatory who am I slide. I'm a hacker. My name's Adam. I founded DC949 a long time ago. Yeah, I'm old. I break stuff. I've been doing a lot with crypto lately, high security apps, supposedly secure systems, and I've done lots of different types of stuff. And I've been founding a co-housing group in Urbana. So if you want to know about that, hit me up later. Enough about me. Rules of engagement. I want this talk to be interactive. So if you have questions, just raise your hand and ask. You don't need to wait until the end. Should I be holding on? Is that what that signal means? Iron Geek? Are you telling me to stop? What's going on? All right. Yeah. All right. I'll keep rocking then. All right. So, yeah, if you have questions, ask. If I'm saying something you're like, that's totally not true, call me out. Maybe I'm wrong, or I can explain what I meant. If you want to learn more, I'm going to be over in the speaker room after the talk. Just come on over. We can get your laptop set up, get AFL running, find some bugs, have some fun. The agenda. So first I'm going to talk about traditional fuzzing, like how it works, old school type, where you're just throwing a bunch of bits at a program and that's that. And then feedback-based fuzzing, which is what AFL uses. So that is way cooler because you get feedback from the target program to know, hey, was this input interesting, more so than did it crash or not. And we go through how to do that with American Fuzzy Lop, just show you how to use it, the limitations, what it can and can't do, show you how it's supported on Windows. There is a fork that runs on Windows, and then show some better approaches to fuzzing, and just wrap up. So this is the traditional fuzzing logic. You generate a bunch of random data, then you choose one of your input files, you mutate it somehow, and then you feed it into your target. So that might be SQLite or browser or Microsoft Word or whatever. And then you're like, well, did the target crash or not? And if it did, great, we won. Now we have something to look into. If it didn't, then, we just choose another input, mutate it in a different way, and, keep on rocking. So the only really feedback you have is crash or no crash. And the problem with this is it misses a lot of interesting code. So, for example, object dump reads in a binary file like an ELF, and the first thing it's going to do is it's going to check the magic bytes, and in an ELF, the first 4 bytes should be 7F ELF. And so if your mutation changes that, it's going to go down the code path of, hey, this isn't an ELF file, exit. And so every time you modify any one of those bytes in any way, you're going down that boring path. But the problem is you don't know that because you don't have any feedback. You just know program didn't crash. So you're going to be going through with possibly 4 billion different iterations on this to, try all the different combinations for the first 4 bytes, and it's just going to be really boring in all of the cases but one. So feedback-based fuzzing fixes that, and looks like my resolution's a little low here, but in the top left, we start, and the thing right below that's AFL Fuzz. That's the program that actually does the fuzzing. It sets up some shared memory off to the right there, and then it runs your target. So object dump, for example. And it runs up to main. And I know it sounds weird because you're like, well, main's the first thing that executes in a program. That's how programs work. It turns out that's not true. There's a whole bunch of stuff that gets done before you actually get to main. So it's going to load all your libraries. It's going to do all the ASLR and move them around. It's going to do relocations. There's all this stuff that happens behind the scenes. And this is all done by libc and your compiler and stuff like that. So you don't have to worry about it as a programmer. But this is all stuff that's happening that takes a bunch of time. So what it does is it runs all that once, and then it freezes the program at main, and then it's going to fork off each time. And so you'll get a fresh copy, and you don't need to rerun that beginning stuff. You just run it once, and then for each iteration that you're fuzzing, you run just the interesting stuff, the main program. So that goes up to main, and then it forks off, and you run your target. Your target is going to be fed, so you have a bunch of seed files. So in the case of Object Dump, a bunch of ELFs, maybe for different architectures, stuff like that. It goes through a mutator and gets fed into your target. And then as your target is executing, it's going to be recording every step of execution, like, oh, it executed this code block and that code block, but it skipped over this, stuff like that. And as it's going through this, it's going to be recording all that stuff to shared memory. So that way, AFL is going to have access to that later on, which is going to be important. So, all right, so you read the file, you go through, and the target then exits. So there's a few different ways that it can happen. The first one we check for is, did it crash? Because if it crashed, save that input, great, let's move on and go to the next iteration. If it didn't crash, you have to ask, did it hang? Did it just like start reading the file and then just never exit? If it did, then AFL will kill it after a certain timeout period, and that varies based on how long your program takes on average. And if it hangs, that's kind of interesting, so it saves all those inputs as well. The reason is it could be a denial of service attack, and most of the time they're pretty boring, but sometimes they're important. If it's like an emergency response system, probably won't actually care about that kind of stuff. So if it didn't crash and it didn't hang, the next option there is if it hit a new execution path. So did it cover new code that hadn't covered before? So in our ELF example, if one of the first few bytes was modified the first time, it'll say, yeah, that's a new code path. And then if the magic bytes don't match the second time, it'll be like, no, that's just the same code we covered last time. It's a different input, but it's covering the same code, and that's just not useful. So we don't need two input files that cover the same code. We can just have one, that's fine. So if it's a new execution path, it's like, cool, save that file, put it in our queue of seed files, and, let's keep going. So once it's made one of those decisions, it's either kept the file or throws it out. And it's going to zero out that shared memory, kind of reset everything, and then fork again for the new target. I just realized people may not know what fork is. Fork makes an exact copy of your program at the point where it is in execution, so at the beginning of main, and it's really, really fast. So that's like I said, you avoid all that execution from loading libraries and ASLR and all that stuff, so it'll go really fast, and you can spin up processes super fast like that. So the key here is the monitoring of execution. And there's a couple different ways that it can be done. You can use a debugger and just set a breakpoint at, every branch instruction, which would be every jump, if statements, while loops, for loops, stuff like that. And then, every time it hits a breakpoint, you can say, okay, the debugger, okay, record that we hit this breakpoint, and then go on. And, and now we hit the next breakpoint 4 instructions later. Okay, go on. And the problem is that's a lot of overhead because you're firing an interrupt, and the OS is doing the interrupt handler, and it's passing off the debugger, and the debugger's saying, oh, what happened? Let me record this. And then the debugger's saying, okay, go ahead and continue now. And you only executed like 4 lines of assembly. This is like way too much work to be really practical. The reason I mention it is because sometimes there's not a whole lot of other options. If you're on like an embedded system, you might not have any dynamic instrumentation. You might not have something that you can emulate. There might be like special ICs on there, memory mapped I/O, stuff that you can't just throw in an emulator because there's an actual chip there that handles this thing, and you don't know how it works. So you don't have any way to emulate it. And if you don't have source, obviously the compiler is not an option. So while debugging's the worst option, sometimes it's the only one you've got. So then you have dynamic instrumentation. That is rather slow for fuzzing. The way dynamic instrumentation works is very cool. So it is its own little program, like Pin Tools is one by Intel, or Dynamo Rio is one by its open source one. And you run your pin tool, which is going to basically monitor execution and figure out what code was executed. And it will read in your input file. So if it was object dump again, it's going to read in the first few instructions of object dump and then kind of rewrite them and put them in its own code cache. And then it's going to execute out of its code cache. And then when it gets to the end of those instructions, which would be a branch, a loop, any kind of jump that's going to go somewhere else in the code, and you're not sure, well, is it going to go here or there? Then it'll freeze at that point, fetch more of the object dump, wherever it's going to go, whatever part's needed, rewrite that, put it in its code cache, and then continue execution. And the whole time it's doing this, it's monitoring and saying, and every time it hits one of those, not quite breakpoints, but one of those stop points where it's going to fetch more instructions, decode them, and re-encode them, it's going to be recording execution the whole time. So this is actually pretty fast if you have a long-lived process. So you're only going to fetch, decode, and re-encode those instructions once. After that, it's going to be in the code cache. So you can just execute out of your cache, and you've already made sure that it's not going to escape and go somewhere else, so you lose track of it. But the problem is with fuzzing, you're going to be running through it once, and then the program exits. And so it's not great at that because you're doing all this fetching and encoding and things, and there's a lot of overhead again. It is faster than the debugger, but it's still pretty significant slowdown. And there's not a whole lot that you can do about that because they're very meticulous. Like, one idea would be to cache that once and then just keep using the same cache. The problem is that's not going to work if you have any just-in-time compiled code, like JavaScript will, compile down to native code, and if you have anything that's packed, like malware or anything like that, that's going to be a problem because it's going to change in memory as it's executing. And so that thing that you cached is now not the right instructions anymore. So like Pin and DynamoReal will handle that, but you can't, it needs to be doing it at runtime. It can't be done offline ahead of time. So the next option is emulation. So run it in a VM. You can do that with an entire OS, which is pretty slow because now you're running an entire OS when really you just want to run one program, object dump or whatever it is. To process emulation, so QEMU on Linux has process emulation. So what that does is instead of running an entire virtual machine, like with an OS and everything, it just runs that one process under emulation. And there's a modified version of QEMU that will record every instruction as it goes through, which is pretty easy to do when you have an emulator that's dealing with each instruction. And if you're doing process emulation, it's actually not too bad. It's about a 2x slowdown on average, so it'll go half as fast as if you're running the program natively. The last option is compiler instrumentation, which is by far the best option. It's going to be way faster. It's the overhead varies depending on different internals of the program you're fuzzing, but that's going to be the fastest because you're doing all of the calculations to figure out how to track it offline. You do it once when you compile it, and then every run, it just runs through. There's no breakpoints. There's no rewriting of binaries. There's no emulator. It just runs in native code, and it writes to that shared memory from the previous slide. The problem is, of course, you need source code if you're going to do that. So if you want to fuzz Microsoft Office and you're not Microsoft, you probably don't have that source code. It also means that your source code needs to build. So if you're dealing with embedded stuff or just source code that's really hard to build, and you're like, oh, I have 2 weeks and I can fuzz this program, and it takes you 3 days to get it to compile, that's not so great. The other thing is the instrumentation in AFL only works on C and C++ code. So if you're doing something in .NET or whatever, then that's not going to be an option either. So yeah. So then, how do you do it? Let's just get down to the nuts and bolts. You download AFL. You use, if you have source code, use either AFL GCC or G++, C or C++, to compile it. And then you have your compiled instrumented binary, and you just run AFL. and that goes through the same loop that we saw earlier. That'll start the target process, freezes at main, forks off every time you're running a new input, tracks everything on shared memory. You have your mutator that mutates all your input files, and if it doesn't find any new code, it didn't crash, it didn't hang, we just throw it away. Like, we don't want to have 8 billion files in our file system. I've written fuzzers that did that before, and it was a bad idea. But I didn't have any feedback at the time, so that was what I had. So here's an example. This is TCP Dump, and I'll just walk through exactly how to read this. Luckily, the print is showing up a little bit better on this one. So at the top left here, you have the runtime. So it's been running for 2 days, 2 hours, etc. And the last new path was found 3 minutes ago. So it's still finding new code. This is a good sign. This means it still might kind of stumble across a bug. Last unique crash found, haven't found any yet. It's TCP Dump. It's been pretty well tested. We found some hangs, and this is using a slightly old version of AFL, so the way they did hang detection was a little bit different. And basically, if it took longer than average by a significant amount, they called it a hang. Maybe it was going to end a few milliseconds later, but at some point you have to say, well, when do I stop waiting? There has to be some kind of a cutoff. And they've improved that hang detection since, and you'll have a lot less hangs because a lot of these are false positives. You'll run the files through. My monitor's going crazy. You'll run the files through, and it'll be like nothing happened. Like it ran through, and like it exited, and everything went normal. But they're getting better at that. It's a kind of hard problem to solve because how long do you wait? How long is too long? Stuff like that. So the other important part is in the top right. Cycles done. I'll come back to that. Total paths that I've got 2,300 different code paths that we can take through TCP Dump. It turns out it's a really complex software because it's trying to parse out IPv6, IPv4, TCP, Ethernet frames, like all the different protocols that I'm running through here are going to be going through different parts of the code. And then you have stuff where DHCP will encapsulate a UDP packet and like all these weird test cases, so you're kind of hitting different codes in different ways. You have your unique crashes and unique hangs in the top right. No crashes, 371 unique hangs. But if you look down here, the total number of hangs is 128,000. And we're running at about almost 200 iterations per second, so that's not bad. 3.2 million executions total. So out of those 3.2 million, 128K hung. These are the different fuzzing strategies. So when I said mutation, these are the different ways that it can be mutated. So bit flips, where you just flip one bit in the entire file. And you're just kind of running through the entire file, flipping one bit at a time, running it through, and seeing what happens. So that one's kind of cool because it hits things like negative numbers. So a +7 just became a -6 or what have you. And all of a sudden it's like, oh, well, I was going to seek forward 7 bytes, but now I'm seeking backwards seeking backwards 6 bytes, and, chaos ensues. Byte flips, same thing, but you're just smashing 1 byte at a time, so you'll replace a null character with, a capital A or whatever. And then you have arithmetics, known ints, and a few others that do just other types of mutations. It's pretty good in terms of the different ways it mutates it. The dictionary one in particular is used when you're fuzzing something like HTML, for example. If you have a tag and it's just an invalid tag name, then it's going to be like, oh, that's an invalid tag. Just drop it on the floor and just move on to the next one. So you might use a dictionary to say, okay, these are all the valid tags. These are the only ones you're ever going to see. Don't bother, with the ASDF tag because it's not a real thing and it's not going to hit any interesting code. So let's just limit it to the tags that actually exist that we know about, and it'll waste less time going through the error cases where it's just going to drop stuff on the floor, and maybe you'll throw in one, bogus tag just to cover that extra piece of code. The other thing that you have here is how much of the code you've covered. You can see there it's less than 10%. And that matches up pretty well with the fact that I'm still finding new code paths after a couple days of fuzzing. And then you have some more statistics on favored paths, new edges, stuff like that, and path geometry. That's getting kind of into the details, but if you want to know more about that, you can ask after the time. Or now.
How powerful was that system? Or how powerful do you recommend using that?
So that system, the question was how powerful was this system that I'm running on? That's a box from a couple years ago. It's a 16-core AMD machine. Each thread of AFL only runs on one core. It actually, when it starts up, it binds to a particular CPU and says, just keep me on this CPU. And the idea there is you get your L2 cache, there's some performance optimizations. I don't remember what the clock speed is on it, 2.5, 3 gigahertz, something like that. It's a decent machine. I'm getting a new one soon. It'll be a 64 core with lots of RAM. I'll be like, yes. Is it possible to use GPUs for fuzzing? Let me think. Well, you can fuzz a GPU because there's code that's executing in your GPU normally. I don't know. I can't think. So the big problem with GPUs is they can do calculations really fast, but their memory I/O, like you have your dedicated memory on board, but actually touching main memory is slow. So I don't know if you can do it, and I don't know if it would be a good idea. Any question?
So, what is the bottleneck? Is the bottleneck the execution of the program, or is it generating mutations?
The bottleneck is almost always in the execution of the program. Yeah. So the mutations, they're really fast. Yeah. So I actually have another example here, which is the XZ utility. Compression utility compresses, decompresses files. And this one has been running for about the same amount of time, and we haven't seen a new path at all, which is usually indicative of a problem like AFL's not working, you didn't do instrumentation right, like something weird is going on. But in this case, that was not true. It's just that it already found 126 paths, and I think I restarted it. So it's like, oh, I already found these 126, and I haven't found any new ones since then. XZ is a pretty simple program. Like, you're going to compress or decompress a file, and I don't remember which. I was doing either one or the other because all the arguments are going to be the same every time I run it. So I think I was decompressing files, and there's like only so much variation that you can do there. Like, there's only so many different code paths. It's a pretty simple algorithm. So the stats look a lot different here. Cycle's done. I was going to come back to that and I forgot. So it's going to go through all of your different fuzzing stuff, and then after it's gone through all of them with all your input files, yeah, go ahead and switch me out there. After it's gone through all of your input files, it's going to say, "Cool, I've done all the possible mutations on all of the input files. Great, that's one cycle." And then it's going to loop through and just go through again. So in the previous one, we were at 0 cycles because I had a lot of input files, and they were, unfortunately, some of them were larger than I would have liked, like, a couple hundred K. So if you're flipping 1 bit in a couple hundred K file, that's, a lot of iterations you need to go through to get through one cycle. On the other hand, with XZ, I only had a couple files that I created, with XZ itself, or I think I used 7-zip for one of them to kind of get a different spin on it. And so I have a small number of files, so it's going to rip through the fuzzing strategies a lot faster, and it's going to get through cycles faster because I don't have a huge variety of files. If I was fuzzing something like 7-zip, on the other hand, which can handle a tremendous number of file types, I would have had a lot more inputs, and it would have taken longer to get through a cycle. Once you see the cycle count get up that high, you're probably not going to find anything new. It's not finding any code paths. We've done a whole bunch of cycles, so we've mutated every which way. It might be time to just, say, hey, you know what? Let's fuzz something else. This is unlikely to result in any bugs, which is good if you use XZ. So that was all with source. So what if you don't have source? What if you're fuzzing RAR, for example? It's a closed source binary on Linux, does file compression again. If you run it with the -q flag, like everything's the same. You don't compile it because there's no compilation step, and you just use the -q flag for running in QEMU mode, and then everything works exactly the same, except it's running in your custom QEMU emulator instead of running, natively. So it's a little bit slower, but it does the same fork process. It tracks, via shared memory. It's all the exact same stuff. So limitations. So there's a lot, unfortunately. It turns out anytime you dig into pretty much any tool, you find out about all of these, like, oh, it doesn't do that, or, it doesn't do that well, or there's a bunch of bugs there. So you might have noticed all the examples I gave were files, reading in a PCAP or ELF file, etc. That's because that's all AFL does. It just deals with file I/O or standard in, standard out, which is really just another file. But there's a cool project on GitHub called Preeny, and what it does is you LD preload their code, their .so file, and it will hook the functions for network functions like accept and receive. And whenever your program's like, oh, read stuff in from the network, what it does is it's like, oh, let me just read some stuff from disk and return it to your program. Like, here you go. Here's all your network data. And so it's a fun little hack that lets you actually fuzz network stuff instead of just file I/O. And that works on Linux, and Preeny will also work on OS X. So that is an option. So yeah, like I said, only standard in or file reads. The other thing is the file head the target needs to read the file, process it, and then exit. If it reads the file and then sits there and looks at you, AFL is going to be like, well, that's a hang. So if you have a text editor, for example, with a GUI, it's going to read the file and then sit there and look at you. And it just doesn't work there. That's one of the limitations. Ways that you could if it's Linux, you might have the source code for it, in which case you can just patch the source to say, oh, load up the file and then exit. And just change the source code to exit every time. If you don't have the source code, you could do the same thing. You would need to do a binary patch. It's, a little bit more difficult. And if you aren't familiar with the program, then, it might be hard to figure out where do I put the exit. Should I put it here? What if, the code path takes a different path and doesn't get to my exit? So it's not a great solution. There is an example with Nginx, which is a web server, where they changed the source code so that it would read from standard in, and it would read a web request, so it would be from a browser. It would process the request and then exit. So it would just handle one request and then exit, and it worked pretty well. They didn't find any bugs, by the way, so spoiler alert. But they were able to fuzz it, and it went through the whole process, and they got a pretty reasonable number of iterations per second. More limitations. It only works on applications. So if you have a driver that you're trying to fuzz, or the kernel trying to find some ring zero exploit or ring zero vulnerabilities, then AFL is not the thing for you. If you're working on firmware, it's probably not going to work. It does run on Android, but that one's actually not that interesting because Android apps are mostly not reading files. So, and they're also not native. It only works on native apps on Android. So it's not tremendously useful, but it does work there. So it might be possible to run it on embedded systems, but you're not going to do the entire firmware. You would be doing a binary that runs on your router or what have you. QEMU mode only works in Linux. So there was an effort to port that feature to Mac OS so that it could run on Macs, and it got abandoned pretty quickly. So that doesn't exist there, and it doesn't exist in Windows at all. Windows uses Dynamo Rio. That was the binary instrumentation that I mentioned earlier that rewrites the binary as it executes. On OS X, there isn't any dynamic way to do it built in. Everyone seems to be using source code. So if you have source code, great, you can use AFL. If you don't have source code, you can port it to use Dynamo Rio like the Windows one does, and that would work. It's a lot of work. No one's done it yet, or at least if they have, they haven't published it. So, yeah. And the other thing is you need to gather all these seed files. There are other fuzzers where that's not the case. The one that springs to mind is KLEE, K-L-E-E, and that one, it kind of generates its own input as it runs. It's pretty cool. But you need source code again, so you're back to that again. So you need to get all these seed files. You need to get a bunch of PCAPs or XZ files or ELFs or whatever you're going to throw at your target. And it turns out that's a lot of work. And if you just make a whole bunch of them with the same program, that doesn't really meet the requirement because they're all going to be made in the same structure. They're going to have the same features. If you're doing images, they're not going to have all the extra, sections of images or like comments and things like that unless you're actually going through and manually doing that as you create them, in which case they might. So you want to use, like if you're generating them yourself, you want to use as many different programs as you can get your hands on, different operating systems, like everything, so that because not everyone's going to follow the spec and not everyone's going to implement all of the things. So if you get a whole bunch, you'll get the most variety, which is what you're looking for. The other thing is the seed files should be as small as possible and they should cover as much code as possible. And you're trying to get maximum code coverage with the least number of files and the least number of bytes. That's going to be your most efficient way because if you have an image and it's a GIF, you're going to have all of this image data. And when your fuzzer is going through and flipping bits or bytes, it'll change a red pixel to a green pixel, and you'll be like, whoop-de-doo. Like, that's almost certainly not going to find a bug. So, like, don't have files with huge amounts of data that doesn't do anything on the code. You want the image to be as small as possible. You might want one image that's, 64K pixels high and like 1 pixel wide, and vice versa, to try and like maybe overflow that with your height and width. But you don't want like this 4K image because most of it's just going to be boring mutations. So I guess I already covered that with the smaller seed files. Juru is a researcher that works for Google. He's on the Project Zero team, and he did talk about fuzzing at scale. And working for Google, gathering input files is pretty easy. He's just like, oh, give me all the fonts on the internet. And he works for Google, so he can do that. So me, I have to go around and manually find sites that have fonts and download them, and yeah, he's got quite the advantage. But he also has different problems than we have, because now he's got like 50 gigs of font files, or whatever it is. He's got, millions of them. And he's like, man, that's way too many input files, and most of them hit all the same code. So he had so what he was trying to do was minimize the size and number of them to get the smallest amount of bytes, basically, to cover as much code as possible. He also changed the mutation strategies, because, like I said, like with HTML, you want to just do normal tags. Well, he had some different requirements, and so he changed the mutation strategies to be more targeted specifically for fonts. And I have a link to the tips, and page 8 has a whole bunch of relevant questions, so you can just check that out offline. It's spot on, though. It's like, did you think about this? And you're like, oh, yeah, that's a good idea. So even when I went through it, having done this for a lot, I was like, yep, that seems right on. So excellent talk. No need to duplicate it here. AFL on Windows. It does exist, and it's kind of terrible. There's a number of reasons for this. One is it's slow because you don't have the fork syscall, so you don't have an easy way to just make an identical copy of a program. And no one's raising their hand telling me I'm wrong, because I'd really like to be wrong about this one, because that is a huge slowdown in performance. And, less fuzzing iterations means slower to find bugs, and nobody wants that. Well, I don't want that. So, yeah, you have all that time for process creation, dynamic linking, ASLR, all that stuff. It uses binary instrumentation, Dynamo Real, like I said. It is dynamic instrumentation just in general, whether you use whatever tool you're using, is going to be slow for short-lived processes. So that's a problem. And then one of the biggest problems that I have with it is you need to manually specify which code to instrument. So with the compiler-based instrumentation, it just instruments everything. Absolutely everything. All your libraries, everything. And if you're using QEMU, again, just everything that executes, it's going to be tracking execution on it. Well, that's not true with PIN. And so I had a great idea. I was like, oh, you want to know what to instrument? I'll just specify every byte of every file, and then now I don't have to think about it, and that's great. It turns out that the performance it kills it. It effectively doesn't work at all. So you actually do need to tell it which code to instrument, otherwise you're going to hit this super terrible slowdown. And that means you're going through, if it's on Windows, it's probably binary. You probably don't have source. You probably don't have symbols. So, yeah, good luck with figuring out what code it is that you want to actually instrument. So one of the targets I was using here was Adobe Reader. And so I just instrumented the acroread.dll file. So I was only tracking execution in the DLL. So if other things were happening in other libraries or in the main program, I would never know. Like, I wasn't tracking it at all. But if different code got hit in the DLL, I would know. And that was also pretty slow, but it worked. I was getting about half an iteration per second, as compared to, you saw the TCP dump was 200, and I think XZ was at 600 iterations per second. So half, 600, pretty big difference. Yeah, and if you have a GUI, which most Windows apps do, then you have to deal with that whole patching to exit or just waiting for a timeout on every single iteration and just ignore all the hangs because 100% of them hang. Question? Yeah, so the question was, is the support for Windows binary only, or do they have support for source? I believe they do have support for source, but you're going to need to compile it with GCC. I think you need MinGW or Cygwin. Cygwin works. Generally, it's not used, but it is there, and I haven't had much experience with it. I'm going to compile a test program just to try it out, and I'm like, all right, cool, it worked. I'm not going to use it, but it was interesting to see. So yeah. So wouldn't it be cool if there was a hardware feature that would just trace execution for us? Well, it turns out on the newer Intel chips, there is. It's called processor trace, and it's in the actual CPU itself, so it's pretty fast. It's not zero overhead, but it's pretty low. It's about 15% or so. And it tracks both userland, so your applications, and kernel. So if you had something that would fuzz drivers or ioctls or what have you, then this would be able to tell you whether new code got hit. So if you're like, oh, run this syscall and then just use different arguments, you'd actually have data that is something that isn't available typically unless you're emulating the entire OS, and then things get kind of complicated. Since it's based on hardware, it's OS independent, sort of. It turns out you need a driver, and the driver basically says, okay, enable processor trace on this processor, limit it to this process ID, put the data here in memory, and when when that memory is full, then call this interrupt, and the interrupt will deal with saving it off to disk somewhere. So it does require a driver, but it's well supported on Linux, and there is a driver in Windows. Still kind of a work in progress, but it's functional, has a bunch of limitations, like all the tools do. And then the other thing is, when you record all this data, it's actually recorded as a taken, not taken packet. So did you take the branch? And so you just have a bunch of bits, so 0, 1, 1, 1, 0, 0, 0. Okay, so you didn't take the first branch. You took the second branch. What branch is that? Well, I don't know. Let me just go through the program and figure it out. So there's a bunch of post-processing you need to do to actually figure out what code was hidden, or what code was hit. You can kind of cheat if you don't really care and just say, oh, well, this bit stream is different than that bit stream, so voila, you hit new code. It's not the best approach, because if you go through like a loop multiple times, then it's going to be like, oh, you hit new code, which, is not true. Yeah, it's a shortcut, and it saves you. When you're doing the post-processing after the fact, it's about 30% overhead, so it's starting to add up. So this addresses the problem of tracing is really slow on Windows, and that you need to specify what code you actually care about. Once the driver gets a little more mature, it's basically going to solve that problem. And it's also useful for future work in the kernel. Should something like AFL be written to do that. So Rich in Seattle is actually the one who wrote this driver, him and his team, and he published it open source, and it's a tremendous amount of work. So greets go out to him. Okay, so sometimes in your target binaries, you're going to get this check, and it's going to be like, oh, does the data equal some magic byte? Or 4-byte sequence or 8-byte sequence. And odds of you just randomly stumbling upon that are pretty low. So if you're going through it manually, and you're reversing the code, and you're like, oh, look, I can see you're going to do a comparison against OX, FO, 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 FO. Cool, I'll just put that in my input file at the place where it should be. And voila, now I hit that new code path that fuzzing probably wouldn't have found on its own. The problem is that you have to reverse the thing and, know how it works, and then you have to figure out what offset in the file was that, and maybe they did a bunch of math and mutated the stuff before it actually got there. So, it's a bunch of manual work, and kind of the point of fuzzing is just, do the work for me. I'll write the tool, and then you find all the bugs, because you can go through code a lot faster than I can, computer. So it turns out there's solvers, SMT solvers, that will basically do this for you. So what you need to do is you need to build basically an algebra problem to send to the solver, because that's really what it does. So the way solvers work is you go through and you're like, okay, read a byte from the network. All right, that byte could be anything. And then there'll be a branch that says, oh, well, if it's greater than 254, go down this path. Otherwise, go down that path. And maybe you didn't hit that. So then it creates two different sets of constraints. One is greater than 254, and the other is less than or equal to 254. So now you have your two different code paths, and then maybe then we're going to divide it by 3, and then mod by 7, and then add, 16 to it, and then if that equals 27, boom, you're great. Okay, well, not 27 because we modded by 16. If it equals 7, then you're great, cool. And it's like, wow, yeah, I can work through all that, but it turns out a solver, if you build all those constraints and, track, it will just give you, first it'll answer the question, is it possible to satisfy this? So if I say x is greater than 5, and then my next constraint is x is less than 5, it'll be like, that's unsatisfiable. There's no way this can ever get hit, so that would be dead code if that were the case in the app. So really, really cool tech, and pretty, this is what the tools of the Cyber Grand Challenge that they ran at DEF CON last year, the automated hacking contest, have been using to find new code paths. Anger is one of the tools that's actually written by Shellfish. That is the team that took second place, and that uses the Z3 solver by Microsoft. It's closed source, but it's freely available, so it doesn't cost anything. Triton is another one. I don't know what solver it uses, but they kind of also do some of the binary stuff for you. And there's an IDA plugin called Ponte, and you just right-click on the place in the code where you want to go, and you're like, oh, generate constraints and solve them, and it'll just generate all the stuff for you and be like, this is what you need to give it to get to this part of the code. And that works pretty well in my experience. There's a whole bunch of other ones. There's, SMT, there's SAT, STP, that's it, which is an open source one that if you're not using Z3, then you're probably using STP. Those are the two main ones. So I was thinking, wouldn't it be cool if you had a REST server? I would just give it a binary name and the target address, and it would just give me a file that would reach that. It doesn't exist. But if any of you want to create it, you should do that. I'll help you. I just don't have the time to do it all myself. So I'm running out of time here, but Driller is the software that the Shellfish team wrote. That's the part that actually finds new code paths. It's open source. It was written by a bunch of PhD students who are really smart, and they get the code good enough to the place where it works well enough for what they're doing. So it's kind of hodgepodge. It's not like production level kind of quality code. So you have to kind of work at it. The other thing is they use it a lot for CTF challenges. And so it's really good at solving these small, tiny little programs that are very, contrived, but it doesn't work on real world binaries. So when you try and run it on TCP Dump, for example, it's just, it breaks. There's some part of the emulations they didn't do perfectly or something. I started digging into it and I haven't quite figured it out yet, but hopefully they'll figure it out, and I'll definitely contribute that back to them because I don't want to run my own fork of their stuff. Question? Does Anger not have similar problems? So Driller uses Anger to do its job, and it does have basically the same problems. Hopefully, Driller and Anger, like I'm one of the people that I'm trying to work on it when I have time and contribute back to it to make it work on real world binaries, at least on Linux. And then once that's stable, then we can move over to other OSs, other architectures, stuff like that. I got 2 minutes. Another one, Fuzzing. It's one that came out. They wrote an academic paper, and they basically changed so AFL kind of blindly modifies bytes, and there's no real connection of what bytes were modified with what code paths were taken, directly anyway. Fuzzing basically fixes that. So we can talk about that after if you want. Open problems in the fuzzing world. GUI interaction, there's no real good solution for it, and it's kind of an NP hard problem where when is the app done processing the file? Well, you can use heuristics to kind of get it, but it's not going to be perfect. There is no network-based fuzzing on AFL on Windows. There's no fork on Windows. We looked into the Linux compatibility layer because you can run Linux binaries on Windows now. So obviously they have a fork, but it turns out those binaries aren't a real process. They're kind of like a quasi-process, so you don't have all the kernel structures that you need there. And so if you want, basically using fork there is not going to help you on normal processes. So if you're running a Linux binary on Windows, then yeah, you can fuzz it, but you could just do that on Linux. So why bother? We looked into writing a driver that would implement fork, and it's far more complicated than it first seems. Basically, Linux tools are great. Windows and OS X, not so great. The academic research is amazing, and the tools, they're awesome when they work, but they're not broadly applicable because that's not really the problem that the academics are trying to solve. They're trying to prove this is possible. And they've done so. So their job is done. And if you want to like use their tools, it's up to you to improve them, extend them, etc. It turns out that's a lot of work, and so academics, they're like, nah, I'm going to move on to something more interesting. That's boring. So this is me. There's some of the bugs that I found. All the ones that I published are on the Not Quite O-Day Friday GitHub account. And I write up like, where did it crash? Why did it crash? Kind of like walk you through. So if you want to learn how these things work, that's a good place to start. And my Twitter handle, I'll post a link to the slides on Twitter. So if you want them, you can get them. And I think I'm out of time. So thank you. So if you want to get some hands-on time, come on over to the speaker room. It's the one in the middle on the other side of the hallway, and we can hook you up, get you fuzzing some programs, find some O-Days, have some fun. Sounds like a good time.